we're going to go over basic trends of the periodic table. The periodic table is organized specifically by atomic number, which is the number of protons. Periodic law states that when elements are arranged in order of increasing atomic number, or number of protons, elements with similar properties appear at regular intervals. So we're going to go over those properties at those regular intervals. Before we do that, we need to know a little bit about the organization of the periodic table just to kind of familiarize ourselves with it. So the periodic table is organized in two ways. One, in groups going vertical. We also call those families because they have a lot in common. And then number two, we call them periods, which are the horizontal rows going across the table. So how you would remember this going down is in groups or columns. Those are the vertical ones. And the period, if you write a sentence from left to right, horizontally, you would put a period at the end of the sentence. That's how I remember that periods are horizontal rows, because you put the period at the end of the sentence after you write a horizontal sentence. The thing to remember is that groups or vertical columns have more in common than the horizontal rows, which are called periods. So groups are more important. Trends in the groups tend to appear as increasing atomic mass, so they start to weigh more, increasing reactivity, increasing atomic radius or the size. And you can see here we're going to go over these specific groups that are highlighted, starting with what are called the representative elements. So the representative elements are the main groups 1A through 8A, which are the colored groups on this picture. It's the first two columns on the left-hand side and then all of the columns on the right-hand side. The center of the periodic table is called the transition metal group, or the transition metals. And then down at the bottom, the two periods going across are the lanthanide and actinide series. We'll talk more about the lanthanide actinide when we talk about radioactive decay, and we'll talk a little bit about transition metals when we get into metallic bonding. The first group is called the alkali metals. So this consists of lithium, sodium, potassium, rubidium, cesium, and francium. This does not include hydrogen. Although hydrogen is listed in the same group on the periodic table, it does not have any similar properties to the alkali metals except for the fact that hydrogen has one valence electron. That is the only similarity between hydrogen and the alkali metals. So alkali metals tend to be soft and shiny. They're very good conductors of heat and electricity. They have relatively low melting point. They react vigorously with water. As you go down the group, it reacts more vigorously with water. And again, hydrogen is not an alkali metal, but it's grouped there because of its valence electrons. Group 2, which is next to group 1, are called the alkaline earth metals. So that's beryllium, magnesium, calcium, strontium, barium, and radium. And these are shiny metals, just like group 1. They're good conductors of heat and electricity, and they react with water vigorously, but not as much as group 1. So group 1 alkali metals react more vigorously than the alkaline earth metals. These are called the alkaline because they tend to form alkaline solutions or basic solutions, which would be the opposite of an acid, when they react with water. We're going to skip all the way over to the right-hand side of the periodic table where we have group 7A, which are called the halogens. The halogens consist of fluorine, chlorine, bromine, and iodine. These are strongly reactive. Fluorine is explosive when in contact with hydrogen gas. And something interesting about this group, it's the only group that includes all three states of matter. Fluorine and chlorine are both gases, bromine is a liquid, and iodine is a solid. So they're kind of all over the place. And these are the elements that tend to form salts. So if you think of salt, you probably think of sodium chloride. Well, that's because it's bonded with chlorine, tends to form salts. The last important group is group 8A, which are the noble gases. These are unreactive, colorless, odorless. They tend to seldomly be found combined with other elements in nature. They like to be on their own, and the reason why is because they have a full valence shell and they have completed the octet rule. Octet rule meaning that they have all the electrons they need in their valence shell. So then let's figure out the differences between metals, metalloids, and nonmetals. Metals tend to be shiny, solids. They can be soft, they can be more firm, depending on what type of metal it is. They tend to be ductile, malleable, great conductors of heat and electricity. They tend to have high melting points and boiling points. That's not always true. It depends on the element. And mercury happens to be an exception to that rule where it exists as a liquid at room temperature. Gallium is another metal that has a melting point of around 85 degrees Fahrenheit. So if you put gallium in the palm of your hand, it would immediately melt because our body temperature is warmer than 85 degrees Fahrenheit. But below 85 degrees Fahrenheit, it would be a solid. Nonmetals have similar intrinsic properties in that they're dull, brittle, low melting point, low boiling point, poor conductors of heat and electricity, and they have low density. So basically the exact opposite properties of the metals. Lastly, you have metalloids. Metalloids are kind of a mixture between metal, nonmetal properties. They're great conductors of heat and electricity. However, they don't heat up as much as metals do, which is beneficial to computers. A lot of the computer chips are made out of metalloid metals, such as silicon. And these elements tend to exhibit properties that are kind of an in-between metal, non-metal structure.